Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about hypothesis testing, which is a very important tool in data science which enables us to determine whether the available data support a certain conjecture. The goal of this video is to provide an overview of the different topics related to hypothesis testing and how they connect to each other. We'll provide details about each individual topic in separate videos. Let's get to it. We're going to give an overview of hypothesis testing. The goal of hypothesis testing, as I said, is to determine whether the available data support a certain conjecture. The way we do this is we take a devil's advocate perspective where we say, maybe the patterns that we're seeing in the data are just due to chance. If this is very unlikely, then we interpret this as evidence in favor of the conjecture. This is the plan for the video. First, we're going to go over the different elements in the hypothesis testing framework. Then we're going to talk about statistical significance. After that, we're going to discuss three very important challenges for the application of hypothesis testing in practice, which are multiple testing, the relationship between hypothesis testing and causal inference, and practical significance. Then we're going to talk about the power of hypothesis tests. And finally, we will discuss nonparametric testing using the permutation test as an example. As you can see, we have a lot to talk about. We're going to be using a running example where we study the free throw shooting of Giannis Antetokounmpo, which is one of the top basketball players in the world. Giannis Antetokounmpo is a really great player, but he struggles a little bit with his free throw shooting sometimes, and he has this very long routine to shoot free throws. When he's playing away at away stadiums, fans taunt him by yelling 1, 2, 3, 4 to try to hurry him up and make him nervous. This does not happen when he's playing at home. So our conjecture is going to be that his free throw percentage is actually higher at home than away. In the hypothesis testing framework, again, we take a devil's advocate perspective and we define a null hypothesis which contradicts the conjecture. In this case, we choose the null hypothesis that he actually shoots the same at home and away. The original conjecture, in this case, is the alternative hypothesis. Okay, so this might be a little bit confusing. We have an original conjecture which we're interested in. We establish a null hypothesis, which is that the original conjecture does not hold, nothing interesting is happening. Then the alternative hypothesis, which contradicts this null hypothesis, is the original conjecture of interest. Now we have to look at the data to see whether we have evidence against the null hypothesis. The test statistic is a function of the data, which should be large if the null hypothesis does not hold. For example, in the case of Antetokounmpo's free throws, we choose a test statistic which is equal to the free throw percentage at home minus the free throw percentage away. If that difference is very large, then this is obviously evidence against the null hypothesis that his free throw shooting is the same at home and away. I just cannot avoid doing like this when I talk about shooting. Okay, so we look at data from the 2021 NBA Finals, and in those finals, it turns out that his home percentage was quite a bit higher than his percentage away. It was actually 23.6% higher. Is this evidence against the null hypothesis? To determine whether this is evidence against the null hypothesis, we compute a p-value from this data, from this test statistic, which is the probability of observing a larger or equal test statistic if the null hypothesis actually holds. If this probability is very low, then we will interpret this as evidence against the null hypothesis. In order to compute such a probability, we need a model for the test statistic. In parametric testing, what we do is we assume that the test statistic depends on a small number of parameters that I'm going to call theta. This enables us to define the null hypothesis a little bit more specifically. For simple null hypothesis, we will say that the parameters equal a certain value, and for composite null hypothesis, we will say that the parameters belong to a certain set. Now let's take a look at how we can apply this to Giannis Antetokounmpo's free throws. For Giannis Antetokounmpo's free throws, we design a two-sample C-test where we model the data as Bernoulli random variables that are equal to 0 or 1, depending on whether he misses the free throw or makes the free throw. And here, the original conjecture is that these data are actually divided in two groups for which the distribution of these guys is actually different. We choose a certain test, and the null hypothesis is, of course, that the distribution of them is the same. Like the distribution of all of these guys is the same because it doesn't make a difference whether he's home or away. We choose a test statistic that is exactly the one that we already described for Giannis Antetokounmpo's free throws, where we have the fraction of free throws made at home for group A minus the fraction of free throws made away. So I hope it's clear that this is exactly the same as the free throw percentage at home minus the free throw percentage away, because this is the number of data points in group A, this is the number of data points in group B. The null hypothesis is that all of these data points come from the same distribution. We're going to assume that the free throws are independent and shot with the same and go in with the same probability. Under that assumption, they are IID Bernoulli, with a certain parameter that we call theta null, because again, this is if the null hypothesis holds. In the video on two sample tests, we show that under these assumptions, we can apply the Gaussian approximation provided by the central limit theorem and obtain a model for the test statistic, which is Gaussian, with mean 0 and this variance. Now we can compute the p-value. What is the p-value? The p-value is the probability that the test statistic is greater or equal to the one that we actually observe. In this case, this is the value that we actually observe. So we integrate the PDF of our model for the test statistic from that value up to infinity, and we get this probability, this p-value, which is actually quite small. You might have been wondering why we have a test statistic. Why the null hypothesis is that he shoots the same at home and away and not the same or less. We have chosen that null hypothesis. That null hypothesis would also be contradicted if he shot better away, but this would not be apparent in this test statistic, which is not very large when he shoots better away than at home. To account for that, if we wanted to, and that's a choice that we could make, we could choose another test statistic, which would be the absolute value of the difference in the free throw percentage at home and away, and that would be sensitive to cases where he was shooting better away. In that case, the p-value would be different, right? Because now the p-value would be the probability that you're here or here, because we're interested in the absolute value of the difference. You can see that the p-value is double as big. We will compare these two alternatives later on when we talk about the power of hypothesis tests. Okay, so now how do we decide whether the p-value, so we saw that for Giannis Antetokounmpo's free throws, the p-value is very small. How do we decide whether it's small enough to be conclusive evidence against the null hypothesis? Well, we threshold it using a significance level that has to be determined beforehand. It's often set at 5%. If the p-value is smaller or equal to the significance level, then we reject the null hypothesis, which means that we believe it probably does not hold, which is evidence in favor of the original conjecture. What can go wrong when we do this? Well, two things can go wrong. First, type 1 error, we can have a false positive. A positive here means that we conclude that the original conjecture is supported by the data. That means that we reject the null hypothesis, but it actually holds. So we reject it by mistake. That's called a false positive. Something else that can happen is a type 2 error, which is a false negative. It turns out that the null hypothesis does not hold, our original conjecture does hold, but we do not detect that. We are not able to reject the null hypothesis. That's a type 2 error or a false negative. The whole framework of hypothesis testing is set up to protect ourselves against false positives. Let's see why. When does a false positive happen? A false positive happens if the null hypothesis holds and the p-value happens to be smaller or equal to the significance level, even though the null hypothesis holds. So in order to see when we get a false positive, we need to compute the probability that the p-value is smaller than alpha under the null hypothesis. This requires characterizing the distribution of the p-value under the null hypothesis, treating it as a random variable and seeing what's the probability that that random variable is smaller or equal to alpha. Well, it turns out that under the null hypothesis, the p-value is actually uniformly distributed in between 0 and 1 in the unit interval. This holds for continuous test statistics and simple null hypothesis, but similar results hold even for discrete test statistics and composite null hypothesis. You have all the details in the video on statistical significance. Why is this a big deal? Because now the probability of having a false positive is the probability that a uniform random variable is smaller or equal to alpha, where alpha is, for example, 5%. And that probability is exactly alpha. So just to make this very clear, this is the probability that, I say here that this is a small detour because we're going to talk about the implications of this for multiple testing, and then we will go back to Giannis Antetokounmpo's free throws. So we're saying that the distribution of the p-value under simple null hypothesis for continuous test statistic is uniform. So what's the probability of a single false positive? Well, we have like the p-value is going to fall somewhere in the unit interval with uniform density. What's the probability that it ends up here? Well, it's exactly alpha. The probability of a single false positive is bounded by alpha, or 5%, if we have chosen alpha to be 5%, which is great, right? Because we have these very precise guarantees on the probability of rejecting the null hypothesis when it holds. We're protected against false positives. This is great. This is great until we perform many, many tests. What happens when we perform many, many tests? Well, then these tests fall in the unit interval. How many of them, when we have many, many independent tests, are going to fall here just by chance, even if the null hypothesis holds for all the tests? Well, alpha, right? If alpha is 5%, then 5% of them are going to randomly end up here, even if the null hypothesis holds for all of them. This is problematic because imagine that there's 100 studies to determine whether pizza cures COVID-19. We know that pizza does not cure COVID-19, so the null hypothesis holds for all of these 100 studies. But just by chance, because the p-value is uniformly distributed in the unit interval, 95 of them are going to be true negatives. We're not going to reject the null hypothesis, but 5 of them are going to randomly end up below 5% if the significance level is 5%, as it usually is in the literature. So you might ask yourself, well, Carlos, this does not seem like a huge problem, right? Because then we'll see that 95 studies conclude that there's not enough evidence that pizza cures COVID-19, and there'll be 5 that conclude the opposite, but that's okay. Well, yes, that is true if all the results are published. But the problem is that it's much easier to publish when you have a result that is statistically significant and exciting. This one is idiotic, right? But there could be, slight differences have been published, unfortunately, in the media, right? So this could be easily picked up by the New York Times. Like this, there's this new cure for COVID-19. You can imagine that that would be very attractive to a journalist. This is called publication bias, and we talk more about it in the video on p-value abuse. But the bottom line is that you tend to hear more about the false positives just because they're more exciting and it's easier to publish if results are statistically significant. All of this, like publication bias, is problematic due to the multiple testing phenomenon. In the multiple testing phenomenon, we carry out k-independent hypothesis tests with a certain significance level. And if we look at the probability that there's at least one false positive among these different tests, we're going to have k-tests, right? So among the k-tests, what's the probability that at least there's one false positive? Well, that's equal to 1 minus the probability that there are no false positives in any of the tests. If we have established the significance level of each of the tests to be alpha, then the probability of no false positives is 1 minus alpha. Okay? So the probability of at least one false positive is going to be 1 minus alpha to the power k, because we have k tests and they're independent. So we have to multiply the probabilities to get the probability of no false positives in any of them. This value, 1 minus alpha to the k, when alpha is equal to 5%, again, which is commonly said to be the significance level, and there's 100 tests, is 99%. So we're almost sure that we're going to get some false positive. What solution can we find for this? Well, we can decrease the threshold on the p-value to ensure that the probability of one false positive stays small. This is called Bonferroni's correction. We explained this in more detail in the video on multiple testing, But the point is that we reduce the threshold on the p-value to alpha divided by k, where k is the number of tests that we're carrying out. This guarantees that the probability of a false positive is going to be bounded by alpha. So if alpha is 5%, we're still guaranteed that the probability that we reject the null hypothesis for any test when the null hypothesis holds is bounded by alpha, even though we're doing k tests at the same time. The bad news is that if k is very large, then this threshold can be so small that it might be very unlikely that the p-value is below that threshold, even if the null hypothesis does not hold. So this will increase false negatives. And that's just a very big challenge in hypothesis testing that we discuss further in the video on multiple testing. Okay, back to the free throws after this detour. In the free throws, we saw that the p-value that we observe, whether we use the one-tailed statistic or the two-tailed statistic, is below the significance level of 5%. So we reject the null hypothesis. Now we need to ask ourselves, what does this actually mean? Does this mean that the fans yelling at Antetokounmpo, taunting him 1, 2, 3, cause his percentage to be worse? Should these fans conclude that they need to keep doing this so that his percentage is lower when he plays in their stadiums? No, we cannot conclude that, because this, like the difference between his free throw percentage away and at home, could be due to confounding factors such as fatigue. Maybe he's much more tired because they have to travel to go to the away stadium, even if they go in their private jet or whatever. Because of this, so this highlights the fact that hypothesis testing does not determine that there is a causal effect underlying the patterns that we see in the data. We have several videos about this, but the issue, the challenge in causal inference is that to identify a causal effect, we need the potential outcome and the treatment to be independent. Otherwise, there could be confounding factors that account for the difference that we're observing. How can we achieve this? We can achieve this by randomizing the treatment. In this case, the treatment is whether the fans are shouting or not. So we cannot really randomize it in practice. This is a big challenge in many applications. But if we manage to randomize it, then this automatically neutralizes the possible confounding factors, as we show in the videos on causal inference. So this can actually be done in practice, and is often done in practice in randomized controlled trials and also in A/B testing. Let's focus on randomized controlled trials. We're going to take a look at the data from the Pfizer trial for the COVID-19 vaccine. Here, more than 43,000 patients were randomly, and this is crucial, divided into a treatment group and a control group. Okay, and then basically there were 8 cases of COVID in the treatment group that received the vaccine, and 162 cases in the group that did not receive the vaccine. We compute a p-value using a two-sample test similar to the one that we discussed when analyzing Giannis Antetokounmpo's free throws, and we see that the p-value is smaller than 10 to the minus 23. It's extremely small. So now when we analyze this, we see that causal inference and hypothesis testing have complementary roles. Can we say that there's a difference between the control and treatment groups? Yes, because the difference is statistically significant by the hypothesis test. The p-value is super small. Can we say that the difference is due to a causal effect? Yes, but not because of the p-value, but because the trial is randomized. So here we see that we need both. We need randomization to ensure that we can assign a causal effect, that we can interpret differences as being caused by a causal effect. And we need hypothesis testing to determine that a difference actually exists and it's not just random fluctuations, because we don't have enough data. Now let's talk about another challenge which occurs in practice, which is that in large-scale trials, tiny differences can be statistically significant, and those tiny differences might not be practically significant. So imagine, and this is a fictitious vaccine trial, that the data for the COVID-19 vaccine trial had been a little bit different. Imagine that in the treatment group, there had been actually 120 cases instead of just 8. then in that case, and we keep the control group patients the same, the control group cases the same. In that case, the p-value is still below 1%, like this is statistically significant. There is a difference between the two groups, but there's not a practical, like the difference might not be of practical significance because the ratio of positive cases is actually just 3 to 4 as opposed to 1 to 20 in the real data. For such a small ratio, it might just not be worth it to develop the vaccine and make this huge investment in both developing and then giving it to everyone, because it actually makes a very tiny difference. The difference is still statistically significant. There is still a difference in the probability that you get COVID-19 if you take the vaccine. It's just that that difference is so small that it might not be worth it. This is the distinction between statistical significance and practical significance, which is crucial in applications. In order to determine whether there's actual practical significance, you might want to measure the magnitude of the effect, which is not captured by the p-value, because the p-value also takes into account how many subjects there are. And if there are a lot of subjects, the p-value can still be very small if the actual magnitude of the effect is also very small, is very tiny. Here, I'm showing you a confidence interval on the probability that people get COVID-19 if they're in the control group and if they're in the vaccine, and also a confidence interval of the difference between them, which you can see is pretty large. So in the case of the actual vaccine trial, it's clear that the effect is large. It's worth it to develop the vaccine so we could all go back to our normal lives. Okay, so now is it enough to control false positives? We have shown that if we follow the steps of the hypothesis testing framework, the probability of a false positive is actually controlled by the significance level. And if we have multiple tests, we can do the Bonferroni's correction to ensure that it's still controlled. Is that enough? Well, it's not, right? Because it's very easy to never have false positives. You just never reject the null hypothesis. You never find anything interesting. But for that, we wouldn't even be looking at the data, right? We want to find true positives. The power of a hypothesis test is the probability of a true positive. We're going to analyze the power in the context of parametric testing. And for that, we're going to remind ourselves that in parametric testing, we have the distribution of the test statistic, which depends on a certain parameter theta. And we're going to define a power function, which is the probability of rejecting the null hypothesis when the parameter is equal to theta. The name power function is slightly misleading because it can happen that the parameter corresponds to the null hypothesis. In that case, the power function is the probability of a false positive, right? Because we're rejecting the null hypothesis, but it holds. And for that, we know that it must be bounded by alpha. We have already shown this when we were discussing statistical significance. So this is not actually the power. The power is when theta actually belongs to the alternative hypothesis. In that case, the probability of rejecting the null hypothesis is the probability of a true positive, which is actually the power. Okay, so now let's use the concept of power. I passed that slide a little bit too quickly. So again, for theta equal in the alternative hypothesis, the power function does give you the probability of rejecting the probability of a true positive. Yeah, I felt that I had accelerated too much there. Now we're going to use the power to compare two tests. We're going to compare the one-tail test in Giannis Antetokounmpo's free throws when we looked at the difference, free throw percentage at home minus free throw percentage away, and the two-tail test where we looked at the absolute value of that difference. Okay, so in order to visualize the power function, we're going to assume that there's a parametric model, that the free throws actually follow a parametric model where there's a certain percentage at home and a percentage away, and we're going to set the percentage at home to be his season percentage, just to make things simple so that we can visualize a function that only depends on the free throw percentage away. Now we can plot the power function as a function of the free throw percentage away, and remember that that power function tells you the probability of rejecting the null hypothesis. Okay, so the first thing that we need to take a look at is what happens when the null hypothesis actually holds. This is when the free throw percentage away is the same as the free throw percentage at home. And what we see is that for both tests, for the one-sided test and for the two-sided test, this the power function is equal to 5%. This is not surprising at all, because we have seen that for a value of the parameter where the null hypothesis holds, which is exactly there, then the power function is actually the probability of a false positive, which is bounded by this guy. In this case, because we have a continuous test statistic, is exactly equal to that guy. Okay, but what happens elsewhere? So elsewhere we see some interesting patterns. So imagine that his free throw percentage away is just 50%. Okay, is substantially worse than his free throw percentage at home. Then here, this probability tells us the probability that we actually detect this with the two tests. And we see that with the two-tailed test, which is below here, the probability is around 50%, even a bit smaller than 50%. For the one-tailed test, it's larger, a bit larger than 50%. So we see that in this region here, the one-tailed test, where we take the free throw percentage at home minus the free throw percentage away, has more power than the test based on the absolute difference. This is a good thing. We're going to be able to detect, we're more likely to detect a difference between the free throw percentage at home and away to declare that that is statistically significant. What is the downside of the one-tailed statistic? Well, when we're here, so for some reason he actually shoots better away than at home, maybe motivated by the taunts, we wouldn't be able to detect this with the one-tailed test. Here you see that the power of the one-tailed test is essentially 0. Why? Because in that case the test statistic is negative and we're not checking for that. But we would detect this with the two-sided test. So this just goes to show that you have to be careful when you're designing your test so that it is sensitive to alternative hypotheses that you think are likely to occur. So if we really don't care about this part here, we really don't think that his free throw percentage is going to be better away than at home, then we would choose the one-sided test statistic, which is why I started with it. But if we think that might occur, then it's a mistake to use the one-sided test statistic because it has no power in that region that we might be interested in. There are more details about this in the video on the power of hypothesis tests. All right, so we have finally reached our final topic. Up to now, we have been discussing hypothesis testing under the assumption that we had a parametric distribution for the test statistic under the null hypothesis. But what if we don't have such a model? What can we do? We're going to show you an example of what can be done that captures the main ideas in non-parametric testing. And we're going to use an example where our conjecture is that burgers in New York are more expensive than burgers in Madrid. The null hypothesis is that actually they're equally expensive in both cities. Our test statistic is going to be the average price of burgers in New York minus the average price of burgers in Madrid, and this is the data that we have. So our test statistic is equal to the average of these guys minus the average of these guys. It's equal to 4.5. All right. So now, the key idea behind the permutation test is that under the null hypothesis, these labels are irrelevant because the prices come from the same distribution. The place does not matter. If that were the case, then we would have been equally likely to see any permutation of the labels, like for example this one, that leads to a different test statistic. Now we can take a look at the test statistic corresponding to each possible permutation of the labels, which again captures the fact that under the null hypothesis, we think that under the null hypothesis the labels would be would not be meaningful with respect to the prices, so we would have been equally likely to see any possible permutation. So these are all the possible permutations. Well, we start here just to show you, right? We were interested in the test statistic for each of the permutations. For this permutation, the average of these guys minus these guys is minus 4.5. Same for these guys. And now we do that for all of them. And now we ask ourselves how many of the test statistics are larger or equal to the one that we actually observe from the data. The logic being is that if very few of them are, then this is unlikely to happen, and this is evidence against the null hypothesis. In our case, there's 4 of them. All right, so this the percentage of the test statistics that are larger or equal to the one that we actually observed is 16.7%. Well, it turns out that this is actually a p-value. So we have managed to set up a hypothesis test without needing a parametric model for the test statistic. What's the problem? The problem is that we cannot usually list all the possible permutations. Here we could because we had 4 of them. In the case of Antetokounmpo's free throws, there's 85 free throws, and the number of permutations is 10 to the 128. Impossible without, even if you had all the computational power in the world. The solution is to sample many permutations to approximate the probability, to approximate the p-value, as in the Monte Carlo method. If you want more details about the Monte Carlo method, we have a video on it. So here, for the data that we observe for Giannis Antetokounmpo, if we apply a permutation test where we sample, I think it's 1 million permutations, we get a p-value of 0.019, which is pretty close to the one that we got from the parametric test, which was 0.011. Just to be clear, this is the histogram of the permutations, and these are the permutations that end up with a value that is like the one we see of the data. This is a value of the test statistic, right? So the difference in home free throw percentage minus away free throw percentage, and then we're scrambling the labels of home and away. And what we see is that out of the million permutations, only 1.9% have a test statistic that is as big or greater than the one that we observe from the data. From this, we conclude that the null hypothesis, this is clear evidence against the null hypothesis. When we look at the p-value function, which tells us the p-value corresponding to different values of the test statistic for this test, we actually see that the permutation test and the parametric test gives us very, very similar p-values, even though in the permutation test we didn't have to design explicitly a parametric test for the test statistic. Remember that for the parametric test, basically we apply the Gaussian approximation provided by the central limit theorem, but this might not be available for certain test statistics such as the median or other test statistics. And this is the power of non-parametric testing. For these specific situations where typically you're comparing two groups, we can actually compute p-values without having a parametric model. There are more details about this in the video on non-parametric testing and the permutation test. All right, so we've made it. What have we learned? We have learned the different elements in the hypothesis testing framework. We have talked about statistical significance. We have discussed some very important topics in practice, which were multiple testing, hypothesis testing and causal inference, and practical significance. And towards the end, we talked about the power of a hypothesis test, which is the probability of actually finding a true positive. And finally, we discussed non-parametric testing, and we showed how to use the permutation test to be able to do two sample tests without needing to find a parametric model for the test statistic. We went very quickly over these topics. Hopefully you got an idea of how they connect, how they relate to each other. Again, there are more details in the separate videos. And that's all I got. Thank you very much.